So hi everyone, I am César, and I'm going to present my work that I did as a postdoc at INSA Lyon. This work is together with Sonia and Mokhtar, which is the head of the LIDIS lab at INSA Lyon, and with Ramon, which is a researcher at INRIA Lille. And the problem I will be talking about is private mean estimation. And so the idea is that you have a set of parties. Each party has a private value that is a vector. It can be like a machine learning model or gradient. And you want to compute the average of all these vectors without revealing sensitive information about each individual vector. So basically, this is quite a simple primitive, but it is quite, you can do quite powerful computations with it by doing local exploitation of data and global averages, such as federated learning, but other not so hyped ones that are very interesting also. So we will use differential privacy to measure our information leakage. And so the main solutions, the classical solutions that are on the classical models are local DP, which it's prepared to a strong adversary, but is quite inaccurate. And the central model of DP, which is much more, which is the ideal kind of the ideal privacy utility trade-offs, but considers a very weak adversary because you can actually trust the central party. So we will actually consider sitting in the middle, in which there is an adversary that corrupts a set of fraction of parties, fraction row of parties. So basically, you have a set of honest parties that communicate with each other through secure channels, but if this honest party sends a message to another user that happens to be corrupted, the information will be compromised. So in this setting, actually, was studied by cryptographic primitives, and so for example, secure aggregation, one of the most important primitives to solve this problem, if combined with DP, can achieve very accuracy that is very close to the model of central DP. But secure aggregation requires a server, and the work of the server is linear in the amount of parties, so it's not a primitive. So despite of the amount of work that you need on cryptography, it's quite expensive, and it's not scalable to a large number of parties. On the other side, you have another family that is done with purely statistical noise. And this is also, the idea is that it generates a correlated structure of noise, which hides intermediate values, but does not affect utility. So this is much more accurate and also quite scalable to a number of parties. But if in this set you have parties that crash in the middle of the computation, this distribution will break, and you will have an important harm on the accuracy. So today I'm going to present a protocol which attempts to keep a good accuracy and scalability to a number of parties, but also deal with the problem of crashes, which is has been quite important, and there have been quite a lot of problems with it. So our protocol is built on gossip protocols. So basically, gossip averaging is a primitive that allows you to compute an average in a fully decentralized way. And the idea is that each party keeps an estimate of the average, and the beginning, your first estimate is your own private value. And at each iteration, you send your private value to an outgoing set of neighbors, and a set of neighbors will send you back their estimate. And you will perform a weighted aggregation on these values to obtain a new estimate. And this, if these weights are well calibrated, you will converge quite quickly to the average. So what have we? So this protocol is fast but not private, and our idea to privatize it depended on three key ingredients. The first two are the most important ones. The first is the addition of canceling noise terms, which are the red noise. And the idea is that you will add on top of your private value some noise that it will serve you to protect intermediate results, but then while you mix with other values, this you will start canceling this noise progressively. And at the end, you will have something that is clean with noise and sufficiently mixed to not expose intermediate information. The second key ingredient is the incremental injection. So the idea is to protect against crashes. You will try to reduce as much as possible the variance of this correlated noise. And how we do it is injecting our private value bit by bit in the computation in the system. In this way, the amount of sensitive information you inject at the beginning is small, and the variance to achieve a differential privacy guarantee is also small. So if you have harms, the harm will be reduced. Finally, you have also some independent noise that is the noise that will remain if there are no crashes. And this is only on the order of central DP. So it's small noise. So we study the privacy of this protocol. So basically, we consider an adversary that sees the weights of aggregation. So basically, we can, with some traffic analysis, an adversary can easily analyze interactions. So we consider this the knowledge of the adversary, and can construct a set of linear relations, a linear system of equations in which the unknowns are private values and noise terms. And basically, if this linear, the more undeterminate is the system, the more privacy you have. So basically what we have discovered for this algorithm is that the set of solutions of this space is quite related to the vector of outgoing edges each party has at each iteration. So basically, we call it this IIT, I for parties, T for iteration, and this vector will determine the set of solutions. And what we actually have have proven is that if there have been index executions, there have been a sufficiently large amount of these vectors whose message has not been seen by the adversary, then you will, and these vectors are linearly independent, the blue noise, that is the one that remains, will be bounded in a way that we will get central DP accuracy or very close to it, if there are not dropouts. If there are dropouts, this will degrade, but very gradually. And we will analyze the impact of the correlated noise empirically. So finally, we have compared with other correlated noise techniques. Some of them, so one of them is very sensitive to the distribution of dropouts. So basically, on the bottom, there is central DP. On the top is local DP. And all other lines are different distributions of this per core, which is the other protocol. And we have less error in most of the techniques, in most of the settings, even in the ones that are very optimistic for the other existing pairwise noise protocols. And this is also taking into account that all other techniques use the same communication. And we approach very close to central DP. And finally, we have also compared with popular secure aggregation techniques, showing we illustrate in runtime how cryptographic techniques, even if they're constant round, given the number of processing they have to do with the number of parties, they have a larger runtime. So that's all. Thank you. And the questions will be in the next session.